In this lesson, you will learn about what's known as the fundamental problem of causal inference. You will also learn how you can use machine learning techniques to be able to determine which patients are most likely to benefit from treatment. To decide whether to give a treatment to a patient, a doctor would want to know what the effect of a treatment on a patient would be. If the treatment is likely to reduce the risk of an adverse outcome like a heart attack, then we would want to give the treatment. If the treatment is likely to not affect, or worse, harm the patient, then we would not want to give the treatment. One possible set of potential outcomes for a patient would be that with the treatment, they wouldn't get a heart attack, while without the treatment, they would. In this case, where the patient's outcome with treatment is a heart attack, while the patient's outcome without the treatment is that they don't have a heart attack, we can say that the effect of the treatment was benefit for this patient. But treatment may not benefit everybody. Some patients may have potential outcomes such that they have a heart attack regardless of whether they get treatment. Some patients might not have a heart attack regardless of whether they get treatment. In both those cases, we would say that the treatment has no effect on the patient. Finally, a patient might have a heart attack with the treatment and not without, in which case the treatment has harmed the patient. We can represent these four possibilities for a patient's potential outcomes using the Neyman-Rubin causal model. For each patient I, we represent their outcome when given treatment with yi of 1, which is 0 when the adverse outcome of interest does not happen, when the heart attack doesn't happen, while it is 1 when it does. Similarly, yi of 0 represents the patient's outcome when they are not given the treatment. Our main feature of interest is the unit level treatment effect, which is the difference between the potential outcomes. Here, -1 represents benefit, 0 represents no effect, and 1 represents positive. And you can confirm that these -0 and 1 correspond to the difference between the first column and the second column. So if we knew the potential outcomes for many patients in a data set, we can compute the mean for each column. So let's take the first column. We have 5 patients, and if we take the average here, we get 2 over 5, which is 4 over 10, or 0.4. And 0.4, or 40%, represents the fraction of patients here who experience an outcome. Similarly, in the second column, we can compute the average here, and we get 3 over 5, or 0.6. And 0.6, or 60%, is going to represent the fraction of patients in the control arm who experience an event. Finally, we can take the average in the third column over here. So we add these up, we get -1 over 5, or -2 over 10, or -0.2. And -0.2 is the average decrease in risk with treatment. So why is this useful? The reason this is useful is because our third value over here is what is called the average treatment effect. Formally, the average treatment effect is the expectation of the difference in the potential outcomes, and the expectation can be given by taking the average of this column, so which is this number over here, -0.2, and this is the expectation of y1 minus the expectation of y0, and we can get the expectation of y1 by looking at the average of this column over here, so that's 0.4, and the expectation of y0 by taking the average of this column, which is 0.6. And we should be able to confirm that -0.2 is -0.4 minus 0.6.